Thank you everyone for coming. I know this is the last session of the conference, so I'll try to not get over the time. So I am Mihai Maruseac from Google Open Source Security team, and I am going to talk about how we can train tamper-proof models on notebooks. So to set up the context, around 3 years ago, a little bit more than 3 years ago, with the advent of ChatGPT, the feature that we saw in sci-fi books and movies became a reality. We started seeing a lot of chat apps, a lot of AI agents helping us write code, shop online, do vision, and so on. But there was still a problem, and that problem is that while everyone was focused on building the top of the castle, all the cool, awesome AI projects, there is that tiny little piece at the bottom that is the AI supply chain security, AI supply chain security. So why is this a problem? Because in general, when you think about deploying an ML application, you think of two steps. There is some training, and then there is an application that uses the model. But actually, there are at least 3 steps. You have a big foundational team that builds a foundation model training on the entirety of the internet, such that the model knows how to respond to text, basically chat interactions. Then you have a fine-tuning step or multiple fine-tuning steps to make the model work with the application that you want to build. And then finally, after many stages, you get the model to deploy the model into the application. You might also quantize the model, transfer the model from one format to another, and so on, but these minimum 3 steps is the one that you need. And you don't have a single person that works in all of these scenarios. You actually have at least 3 separate teams. And in between these teams, they are not taking the model, putting it on a USB stick, and passing it to the other team. They're actually putting the model into storage, into a model hub. So now you have at least 5 different teams where somebody malicious could tamper with the model, and the model that ends downstream is not the model that is intended. And actually, let's do a demo for that. So I'm going to switch to a demo notebook. I'm going to run 2 cells for the setup, where I'm just importing some stuff and defining some functionality. And then once these 2 finish, I'm going to put my hat as a trainer and train a model and upload it to a model hub. So this is a simple model. It's a TensorFlow model that does digit recognition, so MNIST. And once this setup finishes, this section will start running. OK, so now we're seeing it training. I'm just training it for 5 steps because we don't want to spend a lot of time. It finishes, it uploaded to the model hub, so now the trainer jobs is done. Now let me put on the user hat. I download the model and I use it. Basically, I give an image to the model and I ask the model to tell me what digit is in that image. And the model tells me I pass in a 7, which is all good. This works. But now let's actually do the security part. Let's say I am the model hub and I am malicious. So now I'm going to run this hack model function, which actually tampers with the model that got trained. And now if I put on the user hat again, and I try to download the model and use it, this time, instead of getting the digit 7, I get an error message that all the models belong to the hackers. Basically, the user got hacked. So switching back to the presentation, this is what we tried to solve. And this is not just something theoretical. We actually had scenarios in the past in the news where this happened. Furthermore, if you go on Hugging Face and you search for Llama models, you'll see that there are 2 providers for this. One of them is Meta Llama. The other one is Facebook Llama. Only one of these models is the real Llama model. The other one is the security researcher uploading an empty model that just says this model is fake, don't use this. If you just look at the name and the provider of the model, you don't know exactly which one is which. Sure, you can look at the stars, model cards, and so on, but all of these other metrics can be tampered with, can be gamified. And actually, there is a recent study that says that in ML, the models that have more stars are the models that might be more compromised than the models with fewer stars. OK, so going back to the context, 3 years ago, the feature became a reality. AI models started proliferating. We got this Cambrian explosion of applications. But there was no way to verify trust and integrity. And I just show you a demo on how easy it is to hack a model. And traditional approaches wouldn't work. I'm not going to go into details for that. I'm actually going to show you a solution. We have released during this year, we have released a model signing library that allows trainers to sign their model before they upload it to the model hub. And this way, they prevent compromises that occur on the model hub. There are some vanity metrics on this slide, but they are not that relevant. So I'm going to go to another demo, where I switch back to the notebook, and I show you how signing models prevent compromise. So let's train the model again. So I still have the trainer hat on me. I train the model again, and in between, before uploading the model to the model hub, I run this step here where I'm calling model signing, sign, and I give the model and where to put the signature. So this one asks me to identify myself. So I'm going to run a YDC flow and identify myself, logging in with GitHub and pasting this code back to the notebook. So I paste that one here. And now the model is signed, and the model and the signature, everything gets uploaded to the model hub. Now, let's say the model hub user still wants to hack the model, and the user tries to download the model, but also I claim that I produced this model, so I give the user my identity, my email, and I told the user that I signed the model with my GitHub username. And now when the user downloads the model and then tries to verify the signature, so I'm doing model signing verify, this will fail, and it fails because some files are missing, and also there is a hash mismatch for the Keras file in the model. So the compromise got detected automatically. Okay, so all of this is good. We have model signing launched in April 1.0, 1.1 launched a month ago. We have the model signing specification such that people that don't use Python but still want to target model signing, like from Go, from Rust, and so on, can also target it. But we still need to build on top of that. We need to drive adoption. So right now, the NVIDIA Model Hub supports model signing by default. We're working with Kaggle and Hugging Face and so on to also support it there. And we also need to build on top of this work, because what happened now, we only solved the first part of supply chain integrity. We have the integrity claims that say that this artifact, this model, has not been tampered with. But it doesn't say anything about how the artifact got produced. So that is the second part, the provenance claim, where we can say this model has been built from this data set, from this version of PyTorch, for example, this version, and so on. That's something that we want to build on top. And then finally, there are generic ML properties that we can also attest to in a tamper-proof format, where you can say this model performed this well on this data set. And then the trainer of the model can no longer lie saying that, oh, I released a model that beat all of the benchmarks on humanity's last exam, and then when user starts to actually use those, the model doesn't perform well. Okay, so let's switch back to just one single interaction. We have somebody that trains a model. We have the model hub, which stores the model, and then we have somebody using the model. And we show that an attacker on the model hub cannot actually tamper with the model because model signing prevents the compromise there. But now we just shifted the attacker left. What happens if the malicious user, the nation state that wants to compromise users, is actually the trainer of the model? So one way they can do is they train a malicious model, they release it to you, and they tell you, this is a really good model, you can use it for detecting malware, for detecting compromises, and so on. You take the model, you use it, and actually you get malware on your system. So one thing they could do is they say, this is the model, and this is the notebook that proves how I trained the model. But right now, anyone can edit the notebook and can run multiple cells, can run a cell multiple times, can run cells out of order, can delete cells. So actually, let me show you a demo for that. I'm going to show the demo first. So let me switch on to this other notebook. I'm still going to run the setup, so setting the same setup as before. I'm going to train the model, same as before. And now, because I'm still the trainer of the model, I'm also going to hack the model. OK, I need to wait for this to finish. But the idea is here is I'm going to hack the model, and then immediately after that, I'm going to delete this cell. So this is hacked, delete the cell, upload the model. The user takes the model, tries to use it. Of course, the user gets compromised. The user looks at the notebook, doesn't see anything, and doesn't see any hack the model inside it. So they are now suspicious. So what we're trying to do here is actually generate an attestation. Besides training the model, also generate an attestation that tells you exactly what happened when you built the model. And in order to do that, we actually look at how Jupyter and all of this Colab run, where you have the front end, so basically the web interface where you write the code as the trainer and so on. You have the server, the Jupyter server, that mediates the connection between the front end and the back end. And on the back end, you have the IPython kernel. And you type some code in the front end that gets sent to the server forwards it to the kernel executes, and you get back the results. So in order to generate the provenance, we can add some proxy, or we can modify the server directly, or the kernel. So what is important here is to make sure that we can intercept all the code snippets, including bash. Make sure that we can record the order of executions in the cells, hash all of the inputs for every cell, hash all of the outputs, and somehow also record the side effects. So if you have a function call or a bash call that creates files on the disk, record that these are the files that got created by running this cell. And when you record this, you also record their hash, and then at the end, you generate and sign everything. Sign the provenance, sign everything that got generated. And now when you upload the model, you are going to upload all of this metadata, or upload just the model and promise users that if they ask nicely, it can give you the rest of the metadata. So how does this work for the notebook that I showed you as a demo? Well, this notebook that I run in here actually is a copy of a notebook where I actually have this interceptor, where, actually let me allow you to look through that. Okay, add it anyway. So this one shows you all the cells that have run in the notebook. So this was the first cell, which you don't care, that was the setup. And then you can see I run the setup, I run the train model, and then at the end I run hack the model, which doesn't show up in the notebook. So you could imagine somebody writing a verifier that runs the provenance against the notebook and detects the mismatch. Actually, what we want to do here is make sure that this provenance is both human readable, like you can see it in here, but also machine readable, such that when you import a model, you can have your control plane automatically inspect signatures, automatically inspect provenance documents, and you would be able to say, I only want in my organization to have models that are released by, let's say, Meta, that have been built on PyTorch version, let's say some newer version, that have run through, that have been tested on this data set, and so on. And you can specify all of this automatically in some language, like Q, and then the control plane will validate all of the models that you import for you automatically. You don't have to run spreadsheets, you don't have to monitor everything. Okay, going back to the slides. Basically what we want to do in the future, we want to make sure that everything that gets claimed about models, data sets, and other ML metadata like agent cards, model cards, and so on, is tamper-proof. So once it's generated, you can no longer lie about it, you can no longer change it. It is tied to an identity, so you know exactly who made the claim, like who was the author of the model, who was the author of this model card, who was the author of this benchmark run, and automatically generated by the tools that the ML developers are using. We can, for example, generate provenance for models using GitHub Actions, but nobody is training models on GitHub Actions, so that's why we actually have to do it on Jupyter, and on Colab, and on DeepNode, and so on. Once you have all of these tools, once you have all of this tamper-proof ML metadata, we can actually go further. We can use tools from the supply chain industry like bill of materials, so we can generate AI bill of materials automatically by just running a single tool that ingests all of this metadata, analyzes the graphs, and builds out the final AI bomb. Or we can also do automatic incident response. Let's say you are releasing your model to Europe, and Europe has GDPR that says that grants people the right to be forgiven, but also says that data has an end of life. And now you don't know which models do I need to retrain because the data set that I trained the model on reached end of life or not. And this becomes a more complicated problem once you start training models based on previous models. So once you have all of this metadata, you can actually ingest it. You can say in the query engine, like in Guac, you can say, this data set is expiring, tell me which models do I need to retrain. And then those are the only models that you are going to retrain. You don't waste money training models that are still not end of life. You don't risk not training a model that you should retrain and then getting a fine because accidentally you're still using a model that is now illegal to use. And if you want it in a diagram, this is like a diagram on how models get used to applications. So starting from data sets where you iterate on data sets, then you have the training process where you have the data sets, you have the model source. You might start from other models, like if you are doing fine-tuning. Once the model gets trained, you put it into the model hub, and then from the model hub, some model gets elevated to a production model or put back into more training. Once a model is a production model, it can be put into an application. And at every step into this process, there are supply chain risks, like those identified in here. And model signing prevents compromises in the hubs, so in the two green regions. But the rest of the supply chain integrity are going to protect all of the other green check marks, so protect across every step. Basically, each time some ML artifacts get generated, you sign it. Each time it gets used, you verify it. And if you want to get involved into any of this work, there are 2 working groups. One of them is the OpenSSF Open Source Security Foundation. There is an AI/ML working group meeting next Monday at 10 a.m. Pacific time. And under this working group, there are 3 different SIGs. 2 of them are for security for AI. So one of them is model signing that I talked about at the beginning of the demo. And the other one is Safe MCP, which tries to do the same thing for agentic development. So Safe MCP, Safe Agent, Secure Agentic Workflow, and so on. And if you want the other way to do AI for security, like use AI to discover vulnerabilities, use AI to find patches, and so on, there is the Cyber Reasoning Systems, which started after DARPA ICC Challenge. This is also meeting 17th of November, so 2 weeks from now, 2 Mondays from now, at 8 a.m. Pacific. That should actually be 10 a.m. Pacific, sorry for this. I should fix the time. So the second one is 10 a.m. Pacific. And the other working group that where you can do this work is Coalition for Secure AI. It has several work streams. Work stream 4 is for AI, for agentic security. Work stream 1 is for supply chain security. Work stream 1 meets on Wednesdays at 10 a.m. Pacific. And they just published a white paper on model signing that recommends the solution that I showed you at the beginning of the demo. And if you want to get involved in any one of these, you can just join the calendar, find the calendar online. I'm really happy to see you in either of these 2 forums. And I'm going to end with just a single motto that let's make sure that everything that you create today using AI doesn't become security nightmare on tomorrow.